Talking to an AI for the first time feels like magic, but that illusion breaks the moment it forgets your last question. Large language models are inherently stateless. When a session ends, the memory of that interaction vanishes entirely. Every new prompt is treated as a completely blank slate. This amnesia is compounded by two other blind spots. There is the cutoff problem, where the model's knowledge is frozen in time, leading to hallucinations about current events. Then there is the privacy wall, an absolute inability to see internal, proprietary documents. To fix this, developers use a vector database. You can think of it as an external, continuously updating filing cabinet. It sits alongside the AI, feeding it real-time information and giving the model a permanent memory. Without this external database, a language model is a static conversational trick. Connected to one, it becomes an expandable, dynamic intelligence capable of continuous learning. So how does an organization actually feed its private documents to an AI? Retraining a massive model from scratch every time a company generates a new report would cost millions. This flowchart illustrates a secure framework, Retrieval Augmented Generation, or RAG. Instead of altering the AI's training, RAG intercepts your question, searches the database, retrieves those specific facts, and hands them to the AI as the only context to formulate an answer. RAG enables the system to synthesize verified, strictly controlled facts alongside its core language capabilities. But for this retrieval process to work, we have to look at the underlying mechanics. How exactly does this database ingest raw human language and actually understand what it means? This 3D spatial grid shows the process of embeddings. Raw data, like text, audio, or images, is translated into high-dimensional arrays of numbers to capture deep semantic meaning. Notice how the concepts dog and puppy map to coordinates right next to each other, while a word like car ends up far away. A traditional relational database struggles with this. Searching for concepts via exact keyword matches is like asking a meticulous librarian to scan every single page of every single book. Search time grows linearly with the amount of data, creating massive bottlenecks. Vector databases bypass linear reading entirely. Instead of matching letters, they look for physical proximity between data points in that high-dimensional space. Traditional databases are built to search for exact words. Vector databases are built to search for underlying concepts. When you type a prompt, the system relies on similarity search to find the closest vectors to your specific query. As plotted here, the system uses distance metrics. These are mathematical formulas used to calculate exactly how close two pieces of data are to one another. One method is cosine similarity. It measures the angle between vectors, which is highly effective for matching text meaning regardless of how long the actual documents are. There is also Euclidean distance, which calculates the straight-line physical distance between points and is sensitive to magnitude, as well as dot product, which factors in both the angle and the magnitude. These metrics provide a numerical score for similarity, allowing a machine to quantify and compare relationships between complex concepts. But there is still a computational wall. Calculating these specific distance metrics for millions of individual data points one by one is impossibly slow. To solve this, developers use vector indexing techniques. These act as shortcuts, allowing the database to find approximate nearest neighbors without having to check every single entry. This scatterplot demonstrates the inverted file index, or IVF. It groups the vector space into isolated neighborhoods, instantly narrowing the search area down to the closest cluster. Then there is product quantization. This acts as a compression trick, chopping high-dimensional vectors into smaller subspaces to drastically reduce memory usage and speed up calculations. Finally, we have Hierarchical Navigable Small World, or HNSW. This builds a multi-layered graph. The system uses long highways on the top layer to cross the dataset quickly, then drills down to dense local connections to pinpoint the closest neighbors. These indexing tricks form the invisible architecture that makes real-time, zero-latency AI responses physically possible at an enterprise scale. What happens when this infrastructure expands? Managing billions of parameters for global organizations requires a completely different architectural scale. Purpose-built vector databases rely on horizontal scaling. This is the ability to seamlessly add more server nodes to a cluster, distributing the computational load as the dataset grows infinitely. They pair optimized compression with in-memory caching. This stores massive datasets economically while keeping the most frequently accessed queries directly in RAM, bypassing slower hard drives for instant retrieval. Vector databases have evolved AI from isolated, forgetful text engines into continuous, context-aware systems capable of securely interacting with proprietary enterprise data. The capacity to permanently store, navigate, and connect information in milliseconds provides the structural foundation for AI to move beyond static responses.